And okay, today is the 17th. We are right here. We are going to have an exam this coming Wednesday, 8:50, right? 8:50 to 10:50. Just to remind you, reports for lab 5 and 6, I left it for, the other week, 26, okay? So you can concentrate in your exam. And we were talking about electric induction, okay? And chapter 22, let's see if we can start chapter 23 as well, right? Let's see if we'll be able to do that. And going back here to the notes. So what you have to remember. Search. Oh, share the screen here. Today, oh, you didn't see it, right? Let's see if it doesn't look like I share my screen with you. Okay, let me share the screen again. Here you go. Monday, 17th of April, electric induction. Wednesday, the day after tomorrow, exam 2. You must be logged into Zoom and Canvas simultaneously and your camera on, right? Let's today is April 17th, 2023. And what's the week number? Week number 11. Spring break was week number 9. Week number 11. Week number 11. Exam 2 next Wednesday, April 1923. So just like I mentioned before, I'm just going to copy and paste what we have, right? Material, write that. Material for the second exam. Chapters 20 and 21 plus lab 2, 3, and 4 and related notes and videos. What else? Labs 5 and 6 reports for labs 5 and 6 are due of April and to April 26, 7 days after. And let's continue with electric induction. Electric induction. Chapter 22. What you have to know, okay? If you have, I'm going to keep on repeating that again, okay? So you memorize that if you have a closed loop, a circuit, if you have a closed circuit, okay, and somehow manage to change the magnetic flux through this loop, then you induce or generate a current, an electric current. This is the basis for this is a very important, listen, this has very important applications. This has this law has very important applications in our society. Okay, you have generators. Okay, we use this law to build generators, for instance, whether the generator uses hydroelectric power, thermoelectric power, or hydroelectric power, or thermoelectric, or mechanical. Let's put this one, or mechanical, right? Or mechanical power. So at this point in time, you must remember how a generator works, right? Recall how a generator.
No, he's working on both of them.
What's that? You say anything, Randy? I can hardly hear you. Let's see if there is any messages here from you. Okay, no messages. Do you want to say anything, Randy?
No, I'm okay, sorry.
Okay, thanks. Recall how a generator works. The generator is just the inverse of a electric motor. Okay, an electric motor. In an electric motor, you pass current through a circuit, through an electric, through a loop, through a conducting loop, okay? Conducting loop, which is subjected to a magnetic field. And the magnetic field exerts a force in the loop, on the loop, producing a torque that makes the loop rotate. Okay, so basically that's how the electric motor works. Current through a loop, the loop is subject to a magnetic field. Magnetic field exerts a magnetic force, This magnetic force exerts a magnetic torque, we can put that, magnetic torque, that makes the loop rotate. Okay. In a generator, so in this case, you start, input is electric energy, which is the current. Output is mechanical energy, which is rotation. Okay. Now you couple that loop into an axle, you can turn a wheel and move a car, for instance, right? But then there are other ways of doing that too. Many toys are like that. Okay, in a generator, what do you do? In a generator, you have a conducting loop. Okay, subjected to AB field. So the elements are the same, okay? You make the loop rotate about the loop rotates, make the loop rotate about its axis, right? And in the process, the magnetic flux through the loop changes. Okay, according to Faraday's law, according to Faraday's law, comma, a changing magnetic flux induces a current in the circuit. Okay, in a generator, you have a conducting. You have a conducting loop subjected to a B field. You make the loop rotate about its axis, and in the process, the magnetic flux through the loop changes. According to Faraday's law, changing magnetic flux induces a current. And I'm going to, in this case, I'm going to put that in a different line. Okay, here you go. But I'm still going to leave a space. Input is electric energy, output is mechanical energy. So what is going to be here? In the generator, you have a conductor loop. So you make the loop rotate. I'm going to put it a mechanical energy. Mechanical energy about an axis, about this axis. Yeah. And in the process, magnetic flux to the loop change. According to Faraday's law, change magnetic flux induces a current loop. Induces a current in the circuit. Electric energy. Okay. So input is mechanical energy. I'm going to put rotation. Output is electric energy. Electric energy is current, electric current. That's how. Let's take a look at some examples. Okay. Let's take a look at some examples. And we have, I'm gonna do example 6 in the book. Example 6 in the book. No, example 5. Let's do example 5 first. Example 5. Okay. Coil wire has 20 turns. Loops. Area of the coil is 1.5 times 10. 1.5 times 10 to minus 3 square meter. So now we already have area. The field perpendicular to plane of the loop. Okay. So the angle between, so the magnetic flux through this loop is maximum. Okay, at T equal to 0, B field is equal to 0.050 Tesla. And I'm going to put B naught to denote initial magnetic field. Okay. At T .1 seconds, B is 0.060. 0.060 Tesla. Okay, we are assuming that the field increases linearly. The book doesn't say that, okay? Assuming that the field increases linearly, A. Find the average electromotive force induced in the coil. B. Okay. Okay, B. What is the new EMF? EMF if B field decreased from 0.060 Tesla to 0.050 Tesla in 0.1 seconds. Okay, so solution. Just remember here you go, A, right? Coil has the field perpendicular to the plane increases. In this one is decreasing, right? Item A increases, item B decreases. Let's do A first. Solution A. I want that numbering value. I want to put A here. Nope. Okay, didn't help. Let's get someone else in here. Yeah, let's put back there. Wait a minute. I'll get that here. Maybe I can change this one. You start from A, better. Okay. A. A. Solution. Oh, we gotta go for the equation, right? Let's go for the equation. For the equation that you must have memorized. There you go. That's the one here. Minus, nope. That's the induced electromotive force. They usually put this letter here, epsilon, but in reality, it's a sort of voltage, the type of electric voltage. Okay, and let's look at the flux, magnetic flux through the loop. Okay, magnetic flux, and by the way, he didn't say it's uniform field, right? Didn't say it's uniform field, so he's supposed to say that. Let's imagine that. Yeah, he didn't say that. He has to say that the field is uniform. It's uniform, but it's not constant. Okay, it's uniform and perpendicular to the plane of the loop. Okay, what means uniform? That's your uniform means, you know, the same value in space, right? Here we say that the magnet, but the field is uniform, but it's variable in time. Okay, same value in space at a specific we have to, right, instant of time. If you were to illustrate the field, would be something like that. Okay, it'll be something like that. In this case, I make it pointing towards you. Okay, and we have to write down because the magnetic field is perpendicular to the loop, right, to the plane of the loop. That's gonna the flux is gonna be BA, and then we have also this N. N is the number of loops. Number of loops. And okay, so delta, phi is going to be B minus B naught. That's how we put like that. That's how we put it. And then we have this numerical value there, right? Don't forget B minus B naught. There's more. There's more. Right? A and okay. Consequently, my electromotive force, my induced electromotive force becomes, something like that. Cosine of the angle between the two is, the area vector and the magnetic field is going to be 0. Consequently, I don't need to write down cosine of phi there. Okay, cosine of phi, for phi equal to 0 is going to be cosine, the cosine is going to be 1. And delta t is going to be, I'm going to just put t minus t naught, right? T naught is 0. And that's what we get for that. And then you got to put the numbers here. Okay, it's 20. We have the negative value there that comes from the Lenz's law. The difference in magnetic field is going to be 0.060 Tesla. Right, let's take a look here. 0.0, yep, final. That's the final field. 0.050. 0.050 Tesla. The area doesn't change in this specific case. The area is 1.5 times 10 to minus 3. 1.5 times 10 to minus 3 here, square meters. And what goes down here is going to be how many seconds? It's going to be 0.1 seconds. And now you go ahead, do the math. What you end up getting is going to be 0.003 volts. 1, 2, and 3. Now, what's going to be the direction of the current? Okay, if the field is increasing, like in this case, right? The induced magnetic field associated with the induced current must point. Let's see, variable but uniform current. Let's see what's going on. Generator. Let's see what's going on. I'm in the wrong. Okay, I'm the wrong one here. That's the wrong, incorrect illustration. Let's see if I have the right one here. Yeah, now we have it. Let's see. Okay. Should be a little bit more up. Oops. Yeah, here you go. Should be this one. No. VBDT. Wait a minute. There's a. Let's see here. Yeah. Okay. Should be this one. Something like that. Okay. Delta B, delta T is increasing. Okay. So because B is increasing, the magnetic field associated with the induced current is going to oppose the increase in the flux from this direction of the induced magnetic field. You can use the right hand rule and determine that the current is rotating in the counterclockwise direction. And here should be delta instead of dB, okay? I'm going to, since we're not dealing with differential calculus. Now, what about here? Okay, and now we're going to have the other case in which the external magnetic field is decreasing. That's item B. The external magnetic field is decreasing because the external magnetic field is decreasing. Okay, the induced magnetic field must prevent the magnetic field to decrease. Consequently, the induced magnetic field associated with the current is going to point in the same direction as the external magnetic field. And this induced magnetic field is associated with a clockwise current. Let's do the math. Okay, that's item A. What about item B? He doesn't like that. I'm gonna get this. Gonna be just the numbers are going to be different. Good. Same thing here. Okay. The flux is decreasing from 0.06 to 0.05. 0.06 here. .05. No, wait a minute. I want to do it all the way around. I'm just gonna change the signs here. Okay. And then now this number here is going to be negative. Everything else is the same, right? Consequently, you're going to end up having a positive value here for the electromotive force. What does it mean? It means that the induced current is going to be in the clockwise direction here in this drawing. And I'm going to get, nope, it's not what I want. I'm going to change it here for you folks. And it's not positive, it's supposed to be negative here. It's decreasing. This one too. Yeah, this one too is going to be negative here. This is positive, this is negative, good. Okay, let's, I'm going to do the same here, change the notation. Okay. Example 6 I did last time, right? I just didn't put some numbers in there, so take a look on that. And okay, we have induction. Have you heard of induction stoves? Okay, so that's another application of the electromagnetic induction, of the law of electromagnetic induction, Faraday's law. Okay, so depending, so the top of the stove doesn't warm up at all. Okay, so one pot is made of ferromagnetic metal and from glass. Okay, we know that metals are good conductor, while the glass are an insulator, right? It's called an induction stove because the operator uses electromagnetic induction. Just below the cooking surface is a metal coil that carries an AC current that goes back and forth. It's 25 kilohertz. This current produces an alternating magnetic field that changes in time, by the way, to the location of the metal pot. The pot is made of a metal. And now because the pot is made of a metal, it is a conducting circuit, right? It's a conducting material. A change in field across the pot's bottom surface, and an EMF is induced. Because the pot is metallic and induced current is generated, okay? And the metal has a finite resistance, that's important, because of the induced current. The pot is going to be heated up at the bottom. So the current in the pot, at the bottom of the pot, the induced current at the pot is going to bounce back and forth, and it's going to be strong enough to generate heat, which is dissipated in the resistance of the pot, okay? And the fact that the metal is made of a special type of magnetic material, okay, allows you to have such an effect. It's an interesting technology, okay? While you're warming up the pot, the top of the stove doesn't become hot because there's just a current passing there on the surface of the stove. That's Lenz's law. We talked about Lenz's law, okay? That's one application. Another application here of the electromagnetic induction. So how does it work? Let's spell that out, right? It's a conceptual type of problem. Okay, constant magnetic field in a rectangular region of space. Field is directed perpendicularly into the page. Outside the region, there is no magnetic field. The copper ring slides through the region from position 1 to position 2. Position 1 to position 2 to 3, 4, and 5, right? Oh. 3, 4, and 5. Okay, from position 1 to position 2, what do we have? We have this area here. You know, we have the magnetic flux is changing, right? From here, you know, let's make a drawing here so you understand what's going on. I'm gonna need this one instead. See what's going on here. Here you go, this one. We have a magnetic field, not induced yet. Let's do the drawing. Okay, I'm gonna need that. Let's do this step by step. Okay, I don't want this one yet. I don't want this one yet. So let's start with the circuit, with the region first. Let's start with the region first, that we have a magnetic field. I don't want that, and I want to dash it. Here, like that. I'm gonna put a magnetic field in this region. I'm gonna do just like the book has it. Into the board. So I'm gonna copy that. Good. I don't want that yet. P field, and I'm gonna label it as I'll call that external field. It's not variable. It's uniform and constant in time. The field is uniform and constant in time. Okay. in the next slide, what are we going to have? We're going to have, I don't want this guy here because there's no B field there outside this region, right? So now what we're going to have, we're going to have a ring, a copper ring that's falling under the force of gravity. Okay, that's the position one. And I'm going to make a good. Make a ring a little bit smaller. Yeah. Yeah. And then the ring is going to reach. I'm going to put a little bit, shifted here so it doesn't overlap with my magnetic field. That's time equal to 0, time equal to T1. From here to here, there is no change in the flux whatsoever. I'm going to even animate it for you. Go. The first one is here. The second one is here, right? From here to here, there's no change whatsoever in the magnetic flux. But the moment it starts to cross that region with an external magnetic field, okay, there will be a change in magnetic flux. Okay, at this moment in time, the magnetic flux is 0, right? At this moment in time, magnetic flux is 0 as well. But as it starts to pass through this region, I'm going to make a little transparent. No field. Yeah, now we have it. Yeah, you know what? I'm going to leave the way it was. I don't like that dashes in there. The moment it starts to cross the region of magnetic field, we have a magnetic flux that's given by this B field right in here and the area of the circle. Okay? And then as time goes by, here you go. As time goes by, the magnetic flux keeps on increasing because the area of the circle exposed to the magnetic field keeps on increasing, right? At this moment right in here, the magnetic flux reaches its maximum value. Okay, so what's happening right in here? What's happening right in here? You start to have an induced current in this guy. Magnetic flux is increasing. Consequently, the electric current in this loop must circulate in the counterclockwise direction. Counterclockwise direction, counterclockwise direction. We have, let's go another one a little bit here. It's still counterclockwise direction, right? But now the counterclockwise direction is decreasing. And here, no induced electric current whatsoever. And then the loop goes its merry way down, right? With no induced electric current. This is just a conceptual type of problem until it reaches this point here. But now the magnetic flux is going to decrease because the area exposed to the magnetic field decreases as well. Consequently, because the magnetic flux is decreasing, and remember, it's the magnetic flux, now the current must flow in the clockwise direction. Okay, next. It's gonna fall a little bit more. Like here. Okay, that's how it goes. So okay, we can write that down. Okay. That's going to be conceptual example 9, right? Description of what happens. 9:30. Conceptual example 9, the book. And conducting ring in 3/4. Region of uniform and constant B field. Just below it, just below the ring. Okay. So how does it go? One, as the ring starts falling, right? The region falling, the region of constant B field is still below it, and the magnetic flux is 0. Okay. 2, at the moment at t equal to 0. Here you go. Let's put it this way: at t equal to 0, right? The ring starts falling. The region of constant B field is below the ring, and the magnetic flux through the ring is 0. Okay. At t equal to t1, let's call it t1, comma, the edge of the ring starts to penetrate the region of the field of uniform field. Okay, at time t equal to t1, the edge of the ring is about, okay, is about to penetrate the region of uniform field. And the magnetic flux is still 0. Magnetic flux is still 0. Okay. Oops. There's something wrong here with, okay, good. I'm going to put it at T1 minus, okay? T1 minus, just before the ring penetrates the region of magnetic field, okay? That's what the notation that we usually do. At T equal to T1 plus, the edge of the ring is already inside the region of uniform in magnetic field, and the magnetic flux is different of 0. Is different of 0. Okay. At t equal to t2, I don't need to do t minus and t pluses anymore. At t equal to t2, the edge of the ring is already inside, okay, the region of B field and the magnetic flux, and the region of, I'm gonna put this way, okay, and A is small, here you go, delta A, one area of the ring is inside. Let's see, the edge of the ring is already inside the magnetic field, and a small delta A1 area of the ring is inside this field. Consequently, the magnetic flux is different of zero. Simple. This one goes equal. At t equal to t2, now I'm gonna copy and paste this one. At t equal to t2, the edge of the ring is further down, is further inside the region of magnetic field, okay? And an area delta A2, by the way, greater than delta A1. One. Is inside the field. Consequently, the magnetic flux is different of zero, and it increased compared to its previous value. Okay. Going back here. So we are around here, more or less. Here you go. We are more or less here. That would be the delta A2. Okay. Here you go. At t equal to t3 is further inside the region of uniform field. Let's see. No, I want to copy this one here. Is further inside the region of uniform field, and an area delta 3A greater than delta having. So let's see. Having, and let's put it having an area delta 3A. Yeah, having an area here too, right? Delta 3A greater than inside this field. Consequently, the magnetic flux is still different of zero, and it increased again. Increased again. Right? Finally, that will be T4. Finally, at T, this one should be T3. I gotta change that. Finally, at T4, yeah, at T4, the ring is completely inside, completely inside the region of uniform field. Uniform field. Uniform field having an area delta A4 greater than delta A3. Still different of zero, and increase it by the last time, right? But not by the and increased is still different of 0. It increased, but will remain constant until it reaches the edge of the region of B field, okay, of uniform B field. So he go, and the magnetic flux is still 0. Okay, the magnetic flux is different of 0, and it start to change, right? This induces a current. Here, item number 3. Different and increase compared, okay? Start to change, increase compared to its value. We still have an induced current. We still have an induced current, like that. Read again, we still have induced current. Okay. Okay, we still have an induced current here too, but then at time t equal to, the induced current is decreasing, right? At this point, past the center of the ring, the induced current start to decrease. At t equal to 5. Also see again. The other edge of the region of the field at t equal to t, the ring is completely inside the region of the field, having an area. Let's see what they're going to do here. Delta 4 constant, right? Constant inside this field. Consequently, the magnetic flux is constant. And there is no induced current. Okay, T5 starts here, right? So here, T1, T2, T3, T4, right? Definitely 3, 4, 2, T5 is here. T4, T5, okay. And then T6, T7, T8, okay. Between T1 and T5 and T4 and T4. Let's see, not between T1 and T4, between T1 plus, okay, between T1 plus and T4, between T1 plus and T4, the magnetic flux increased, right? Going back here again, what's going to be here? The magnetic flux increased. Consequently, the current is counterclockwise. The induced current, consequently, the induced current is counterclockwise. Counterclockwise CCW. Okay. between T5 and let's say between T5 and I'm gonna put T6, okay? T6 minus, I call T6 minus this one here. This one here I call T6 minus. Between T5 and T6 minus. Magnetic flux did not change. Consequently, induced current is 0. Okay. At T6 plus, okay, just outside at T6 plus, just outside the region of the field. Magnetic flux start to change again, but it starts to decrease, and the induced current will be clockwise until the ring is outside the region again. The magnetic flux becomes 0 and the induced current goes to 0. Okay? So that's how the whole story goes. Okay? Go magnetic flux, induced current becomes clockwise now. Magnetic flux decreases, right? And now it's exactly equal to 0. At this very moment, the induced current becomes 0. That's what this example is all about in the book. Okay? And this 9, any questions about that? Example 9, okay. So let's take attendance now. The chain save. And that's my Randy Bautista. Are you there?
Yeah, I'm here.
Thank you. Vanessa, are you there? Vanessa Bonilla. Okay, thank you, Vanessa. Ashley Diaz, are you there? No, see Ashley. Okay. Natalie, are you there, Natalie? I see Natalie listed here. Hello, Natalie. Okay, I can hear from her. I'll put a star. Janet. Thank you, Janet. Noor. I don't see Noor here. Noor Hassan. Nope. Okay. Blanca Hernandez. Thank you, Blanca. Kaylee Hernandez. Kaylee, I don't see Kaylee either. Kaylee Hernandez. Joshua Jimenez. I don't see Joshua either. Huh? Joshua, no. Alondra. I see Alondra here.
Present.
Thank you, Alondra. Kennedy.
I'm here.
And
Thank you.
Professor, there's no one in the waiting room because I know I saw Nor earlier.
No, there's nobody.
That's weird. Okay.
Yeah, I don't see Natalie Espinosa. Okay, thank you, Natalie. Next is David Mariscal. So she got kicked out. Okay. Okay, whenever she log in, I will give her attendance. Okay, Daisy, are you there? Oh, yeah. Okay, yes, you're here. Thank you. Yesenia? I see Yesenia here. Thank you, Yesenia. Ryan Ong. Ryan. Okay, thank you, Ryan. Artur Pacheco. Artur Pacheco, are you there? I see Artur Pacheco in my list. I don't hear any interacting. Let's go to the next one. Is Lebilud?
I'm here.
Thank you. Donia? Hi, Donia. Cannot hear you. Okay, so I'm gonna put a star here on Donia as well. Elika? Elika Vape. I see Elika as well. Either talk through the mic or type there in the chat box. I can't hear anything from Elika, so I'll put a star here too. Brianna. Thank you, Brianna. Next is Justena. Justena Youssef. Thank you, Justena. And we have a total of.
Professor, I'm here today.
Who's that?
Donia.
Donia. Okay. Donia. Anybody else? 14, 16. Yeah. Arthur, are you back, Arthur? Or Elika, are you there? Okay, so let's wait for Noor, right? Noor is not on my list. Yep. Okay, so 9:55 right now. So what we did right here, just to give you an idea, all those 10 steps, just what we call a script, okay? For writing a movie, whatever type of movie it is, people go through all those details so they know exactly what to do during the recording, right? During the filming. So that's what we call this thing here, is the script. Okay. If I want to make a movie out of that, already have the script and already have what we call here the storyboard. What you have here is the storyboard. Okay. The storyboard, by the way, was invented by Walt Disney. I discovered that recently. That was one of the reasons the guy became so famous, right? And that's why his business still going well today. Okay, so what we have here again is a storyboard. Well, every time that you're going to film a movie like an Avengers, it doesn't have to be an Avengers movie that's hundreds of millions of dollars, right? It can be a small movie too. You have to have both the script and the storyboard, so you can pass your idea to the actors, to the producer, right? To the guys that are going to finance your work. So I have like 4 videos of my lab. I had to do all of that. I had to do the script and the storyboard. The script, what I was going to say in the camera, right? And the storyboard, what would look like. And then from the storyboard, we make the moving images. The moving images. That's why it's called a movie, right? Because it's moving pictures. Movie is short for moving. Okay, so let's go for our break. It is break from 9:56 a.m. to 10:11 a.m. I see you in 15 minutes. Okay. Get back here and see what we have to cover again. So let's take a look here at the. Okay, we're not gonna cover that in detail. I want you just take a look at yourself, okay? So you can understand how you can reproduce the sound using electromagnetic induction. The speakers use electromagnetic induction and electric generator. We talked about the electric generator, right? We went through that. I even, wrote about it. And we have, let's take a look here at this one, 22. Okay, mutual induction. We want to talk about that. Mutual induction and self-induction and self-inductance. Okay. Okay, so what you have to know about that. Okay. Let's take a look what we have to know about that, right? So mutual induction and self-inductance. Okay, we're going to concentrate on self-inductance. That's more important. And they have mutual inductance and self-inductance. They have different letters. Okay, so here you go. What we have, so you can understand what's going on. Okay, here we have a circuit that's connected to a generator. A generator that we call it AC generator, just like we studied before. So this inductor or this coil or this solenoid has a current that's going back and forth right here. Okay, and because it has a current that's going back and forth, we also have a uniform magnetic field inside this coil. Remember, right? The solenoid is a device that generates a uniform magnetic field. But because the current is changing as the current moves back and forth, the magnetic field also changing time, but remains uniform. That's an important difference. Okay, the value of each of the magnetic field at each point in the cross section of the solenoid is the same at a given instant of time. That's what we mean by being uniform but variable in time. Okay. Okay, because this magnetic field of this coil is changing as time goes by, this secondary coil feels a magnetic field that changes in time, and because of that, there will be an induced current in the secondary coil. Okay, so there is a quantity in physics called mutual induction. Okay, that's defined in the following ways, defined right in here. Okay, let's go. Let me see if I have a drawing here for you for that. Yeah, unfortunately, I don't have a drawing for that. But let's just write down Faraday's law, right? So refer to this drawing right here. And I'm going to zoom in as well. No, no. I shouldn't have done that. Okay, emotional magnetic flux, Lenz's law, electric generation. Here you go. Mutual induction. Wait, I'm back here. And why is it doing that? Yeah, we gotta leave this way. All right. Okay, so let's get the first thing that you have to know, the first thing you have to know. Okay, so let's see, consider two solenoids. The first one, we call two solenoids. One is connected to a generator, which is generating a sinusoidal current. And a second one that is just a closed circuit with no power source whatsoever. So the generator whatsoever. The generator is a power source. Okay, don't forget that. Generators are power sources with voltages that vary, not voltages, but voltage that varies sinusoidally. Remember that in the generator, we have that device that's rotating the magnetic field. That device that's rotating the magnetic field produces the sinusoidal current. And by the way, that device that's rotating the magnetic field also have a uniform angular velocity. Okay? That's how we build those generators. We build the generators coupled to a mechanical source that makes the coil rotate with a uniform angular velocity. Generator, so going back here, with voltage that varies sinusoidally. Okay. Or the induced voltage, you can write down that the induced voltage is going to be, V naught sine of omega t. Okay, like that. Angular velocity. So not only we have this induced voltage that V naught sine of omega t, we also have a current that passes through this device that's going to be I naught, okay, sine of omega t, according to V equal to Ri, so it should be V naught over V naught over R. Okay. I'm not even gonna put V induced. I'm gonna put V so you don't mix up with the induced current in the secondary coil. Okay, we do this way. And I'm gonna put this as a function of time. This one is also as a function of time. In the United States, this V naught used to be 110 volts, 120 volts. Sometimes you need 220. Mostly around the world is 110, 220. Okay, depending on the device that you're connecting to the electricity. Okay, so that now I'm going to even put the primary. Okay, I'm going to put it here. The current, the voltage in the primary, the current in the primary, just like we have in this drawing. Okay. Now, what else? What else do we have to know? Okay, you have to know the following. Recall that the magnetic, the B field in a solenoid is uniform, right? It's uniform. And given by, what's the magnetic field in a solenoid? B is equal to what? N, right? Mu naught. Yeah, oh man. Mu naught. And by the way, I as well. Do you remember that? Uniform magnetic field, right? Let's go back to that derivation that we got. Make sure that everything is right. And we're talking about number of loops per unit of length, right? Instead of looking at my notes, let's take a look at the internet. It's gonna be quicker instead of looking for it in that magnetic field of a solenoid. What you cannot forget is that the magnetic field of the solenoid is uniform. That you cannot forget. Inside the solenoid is uniform. Okay, what's the equation? Here you go. IL. Yeah, that's right. Exactly what I wrote in there. Mu naught. N is the number of turns, right? That's supposed to be divided by L here. Is the number of turns this one? Yeah, it's supposed to be divided by L here. There must be a mistake in this guy. Solenoids and let's take a look at Wikipedia. Solenoid, Wikipedia. We put multiplier there. Solenoid. Physics. Mu naught. Yeah, see that? Wikipedia is exactly what I put in there. Big N divided by L is the lower n, the small n that you saw in there, okay? So there's nothing wrong right in here. Okay, and now how do I find out the magnetic field here inside of this primary coil? All I have to do is to, put my I right here, okay? So I'm going to write it down. The magnetic field of the primary coil is going to be directly proportional to the electric current in the primary coil. If the current is a function of time, so will be the magnetic field. Okay. For the sake of this course, okay, the magnetic field will always be proportional to the current, okay? For the sake of this course, it doesn't matter what is going to be the geometric configuration of your device. It doesn't matter if it's a solenoid, it doesn't matter if it's a toroid, it doesn't matter if a infinitely long wire. The magnetic field will always be proportional to the current, whether the current is constant or not. There will always be a term here in front of my current. Okay. So because we have this magnetic field that changes in time, because we have this magnetic field this B field that changes in time in the primary coil, comma, the primary coil will induce a current in a secondary coil that is nearby and is not connected to any power source. Okay, and that's exactly what you have there in the drawing. Coil. This magnetic field here that's changing in time is inducing a magnetic field in the second coil. So what we have, you're going to have going back to the law of induction, going back to the law of electric induction. Okay, we're gonna have something like that. Electromotive force, the induced electromotive force is going to be the change, the induced electromotive force in the secondary coil is going to be equal to the change in magnetic flux in the primary coil. And here I'm going to put N primary, right? N primary. Don't forget this primary has some turns there inside. Okay. And but we can also write. Here you go, exactly what the guy did here. Oh, don't forget, let's see here. This law. We can also write that let me put it aside so I can use the whole screen. Oops. Get into trouble here. Bear with 1 minute, please. There's something wrong here with my connection to the book. Oh, finally worked. Yeah. Okay, good. Okay, so here you go. Well, but we also have the following. Okay, we also have that this other side here of my equation can be rewritten as the number of turns of the secondary coil is going times the magnetic flux, the change of magnetic flux in time is also going to be equal to the induced voltage in the secondary coil. You see the equality here that we have, right? That's also going to be the same. Okay. So consequently, what's going to happen here? We can here write in the following way. We can pass this term here inside to this other one. I'm going to put them between parentheses. We don't need the drawings anymore, right? That's why I'm gonna pass. I can pass this NP here as well to the inside of this delta. There's a reason for that. Just rewriting the equation in a better way. Okay. And we end up having, you know, something like that. This term right here equal to this other term right in here. Okay. Wow, electricity went out here, came back. Good. I'm not disconnecting from you. Oops, went out again, but that's okay. We're still logged in. Man, let's see this. What's going on here? Okay, so, and now what else do I have to know here? Okay, I have to know the following. There is this definition of mutual self-inductance. And recall that what I have here on the right side, you know, is going to be always something proportional to a current, because every magnetic field, let's not forget, right? It's what do we have here? We have the magnetic flux is going to be B of the primary times the area of the primary, right? But let's not forget that the B of the primary is always equal to a geometrical parameter of the inductor times a current. Okay, that's what you have right here. And I'm going to put it here, C of the primary, okay, and I of the primary. Like that. And if we rewrite this term here in a different way, you know, everything else that you see here, we call, you know, the mutual induction between the mutual inductance between the two solenoids. Okay. So what we end up having here is going to be something, oops, like that. That's what I call the mutual inductance, which, by the way, ends up being all that stuff that you see here divided by IPO. That's what the mutual inductance is all about. Okay, and here writing my Ohm's law. And now we can here write my Ohm's law, which is this one right here. What is end up being? It ends up being the induction in the secondary coil is going to be proportional to the negative of the mutual inductance times delta I in the primary divided by delta T. Okay. That's another way of here writing. This is another way. This is just another way of here writing Faraday's law of induction. And now I'm going to do something else too. I'm going to compare. Now I will compare the above relation with the ones for the capacitor and the resistor. Okay, so recall that the voltage in the capacitor, right? I'm even gonna put a C here so you can remember I'm talking about the capacitor. So what's the capacitance? The capacitance is what? Is the charge divided by the capacitance, right? Remember that? Capacitance is Q divided by C. But I'm putting the lowercase c here so you can remember. What about the relation with the one for the resistor? I want to put all those relations side by side. Is the one for the capacitor. For the capacitor, was the both relations for the ones for the capacitor and the resistor. Okay, that would be for the capacitor, and now when I'm good for the resistor, I'm going to put here resistance is going to be V go to Ri. Ri is what? Ri, right? Here, I'm going to write down Ri specifically. Ri is what? Ri is delta Q over delta T, T, right? Make sense? And now let's take a look here at this relation. Here you go. It's going to be a constant with a negative sign, and we have delta I P delta T, which, by the way, is also delta Q over delta T, right? I'm going to put that between parentheses. And I'm going to even put like a delta Q sub P, right, of the primary. And I'm going to denote it in another way too. If you pay attention, you can see that there is a logical progression here. So if you forget this relation here, you'll be able to remember those. But you remember either this one or this one, you will be able to get to this point here. How? Take a look what we have here. What we have here for the Q is nothing but, you know, a delta Q over delta, and I'm gonna put you know, a delta Q over delta P, but it's not just any delta Q over delta P, but it's a delta Q over delta P raised to the 0 power. Can you picture that? Okay, I'm gonna take it out of. Okay, I'll leave this way. If you raise this delta to the 0 power, this delta becomes 1. If you raise this one here to the 0 power, it becomes 1, 2, and you get back to this equation. And look what we have. Here we have a delta raised to the 0 power. Here we have a delta raised to the first power. And here you end up having a delta raised to the second power. Do you see how this thing is progressing? I can even here write that like that, you know. Delta raised, just another way of here writing the same thing. Okay, here you go. So if you forgot, and they are all proportional to a parameter of the device. Here is a parameter of your capacitor, that is the capacitance or the inverse of the capacitance. Here is the parameter of your device, of your resistor, which is the resistance. And here's a parameter of your other or third device, that is the mutual inductance. If we repeat that for a single device that is inducing itself, okay, then we end up with a similar equation that we call with a parameter, a similar equation with another parameter that we call the self-induction, self-inductance L, self-inductance L, or, go. Now suppose that we have just one resistor. Okay, here you go. Suppose that we have only one coil right now, okay? What's going to happen? This coil itself, because we have a change in the magnetic field here, is going to also, not only are going to have the current due to the generator, but it's going to also have a induced current because of the changing magnetic field inside it. Okay, and if we repeat that for a single device that has a a current that changes in time, or that's connected, let's see, that's connected to an AC generator, and has a current that changes in time, we can say that it also induces a current on itself. Repeating the above, we end up with a similar equation with another parameter that we call the self-inductance L, or you go self-induction is going to be blah, 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 L here, where my L, just like for the mutual inductance here, is going to be given, not this one here that I want, where my L is going to be given, and now I don't need to put the secondary here, right? Because we have just one circuit, N times the magnetic flux divided by the current. One more thing, don't forget that the magnetic flux for the solenoid at least is going to be BA, right? And let's not forget that this B, no matter, is going to be directly proportional to the same current, which is going to cancel out here at the top. And what we end up having is just like the capacitor and the resistor, the inductance, the self-inductance, is a function only of the geometric parameters of the device. Here's a geometric parameter, here's a geometric parameter, and you also gonna have some geometric parameters right in here. If we apply the equation for the solenoid in the above result, right? We get gonna be like that. I'm gonna need only that. Go. The B is gonna be what? The B is gonna be mu naught times N, divided by L, right? you go, and divide by L times what? The current. I'm going to separate them so you can clearly see that what you have here is the magnetic field. Okay, and now what happens to the current? Here you go. Oh, the current, this current here cancels out, right? And I'm going to here write that like the following. Mu naught I'll put here on the front, and the N combined with the big N combined with the other big N, we get that. Okay. So we're going to put them side by side. You know, resistance, capacitance, and inductance. So that's where the idea of inductance comes from. Recall, okay? Remember at the beginning of the course, remember at the beginning of the course that I told you we have four, right? 4 basic devices in electricity and magnetism. Electricity and magnetism. Magnetism. What's that? 1, the capacitor. 2, the resistor. 3, the inductor. And the final one is the transistor. I'm going to even put them in capital letters so you understand that those devices are very important. You can build any device that you want, cell phone, you know, LED screens, using all those 4 devices, simple devices. All those, in this course, we're studying only those 3. This one is for a more advanced course, okay? So let's take a look at capacitance of a parallel plate capacitor, right? Remember, we calculate that before. Capacitance of parallel plate capacitor was what? Epsilon naught. What else? Area divided by distance, right? Let's make sure that I memorize it properly. Here you go. Capacitance of a parallel plate capacitor. Parallel plate capacitor with uniform electric field. Okay, A divided by D. Good. What about the resistance? Well, we saw that the resistance of a resistor is what? The resistivity, right? Times the length of the device divided by A. Okay? I don't need that anymore. Just like before, depends on the geometrical parameters of the device and a constant that depends on the material. Here too, geometrical parameter of the device and a constant that depends on the material that's inside the capacitor. Okay? And finally, what we have for the inductance, we have a similar equation. And I'm going to put these constants here outside so I can separate the parameters with the geometrical characteristics of the device, right? What we have here? Similarly, right? Geometrical characteristics of the device and a constant. Take them side by side. Okay? And I don't want a capital L here because I don't want to mix up with this L, this capital L for inductance. So look what we have, right? All those 3 devices, even their own equations behave sort of the same way. The equations are different, the devices are different, but even the parameters that that quantify that device in all the three cases depends on the geometrical parameters of the device itself. Okay. Note that although these are completely different devices, we have relations that quantify their characteristics in terms of their geometrical parameters. Parameters plus a constant. Okay, constant that's also, that is also inherent to the device. Epsilon naught is a constant of the dielectric inside the capacitor. Rho is a parameter related to the resistor because it's the resistivity. The resistivity changes from material to material. And mu naught is also a constant related to whatever is inside my inductor. Okay? So those are the three very important devices that you have to keep in mind. Okay. And now we can come up with the energy stored in the. What is the energy? What is the energy? Energy stored in the inductor, right? Okay. For the capacitor, we already know. For the case of the capacitor, we already, oh, not this one here. The energy is stored in the capacitor, right? Half C V squared. And by the way, we also know that unit of energy per volume is going to be what? Half. We found that epsilon naught E squared. For a capacitor, we have okay, we have that. For an inductor, we use a similar reasoning. Okay, just recall that the potential energy, we always go back to our basic definitions, right? We always go back to potential energy, potential energy difference divided by electric charge is what is electric potential, right? It's electric potential. We always go back to that. I'm even going to simplify the equation by eliminating this delta right here. So if I want to know the potential energy stored in an inductor, just like we did for the capacitor, we gotta multiply Q by V. By the way, this V here for the inductor is going to be the induced voltage. The induced voltage. And we gotta apply here a negative sign because the potential energy is minus the work done, right? So apply here the negative sign. And I'm going to put also, a delta Q here, just like the book is doing as well. Delta Q Oh, delta Q. Delta Q. Okay, I know that the induced voltage is going to be given by Faraday's law in that different format that you saw, minus L delta I over delta T, like that. Notice that the negative sign cancels out. Let's cancel out the negative sign here, delta. And there is one more thing, one more neat thing. Okay. I can move this delta T below the delta Q. So instead of writing delta I over delta T, I'm going to write delta Q over delta T. Okay. And then what we have here? We have I. Li delta I. Okay. That's the work done by the generator to increase the current. Okay, the work done by the generator to increase the current, and don't forget delta well, now from here to, but that's just a small amounts of potential energy, okay? That's important to keep the delta U here. Okay, if you want to, just like before for the capacitor, okay? The net energy to completely charge your inductor will be given. I'm not deriving it here, okay? I can do only as much here, right? It's given by, the net energy is going to be kind of a similar equation. And we have something similar for the capacitor. To really derive this thing here that I'm doing for you, we need the integral calculus, okay? But it's going to be something like that. Now compare this relation with this other relation here. Okay? Half, the parameter of the capacitor, the parameter of the inductor, V squared, I squared. We have V squared here because the energy of the capacitor is stored in the electric field. We have I here because the energy of the inductor is stored in the magnetic field. Remember, the magnetic field is generated by a current, right? We can repeat, we can here write the above equation for the solenoid as what? Just remember what L for the solenoid is all about. That's the L for the solenoid. I'm going to write that down here. L for the solenoid, go like that. I'm going to rewrite it in a different way, just like the way it's written in the book. So what we have here, we have n squared. I'm gonna put L squared downstairs, and then in order for the equation to remain the same, I have to multiply it by L as well, right? So what we have right here is going to be my lowercase n squared, just like we have in the book, which is the number of terms per unit of length. Okay? There is more. Here's the area of my solenoid. Here's the length of my solenoid. The area of my solenoid times the length of my solenoid is going to be given by the volume of the solenoid. I'm going to write it down as a little v. And also, do not forget that the magnetic field of the solenoid, I'm going to rewrite this equation in a different way again. Okay? Don't forget the magnetic field of a solenoid is mu naught, right? And mu naught. No, it's not n, lowercase n. It's lowercase n times I. Okay? Lowercase n times I. I'm going to put my B field here inside. So in order to do that, I have to rewrite the I in terms of the B. So what happens here? This term goes downstairs. And then what are we gonna do? What's gonna happen when we do that? We did something similar for the capacitor, remember that? Okay, so here we go. My B goes here inside the I. I'm going to put a parenthesis right here. I will erase everything else. What else? Don't forget that's the volume. That's the volume. This mu naught will cancel out with the other mu naught. And we are going to end up with a mu naught downstairs here. One of the mu naughts that were inside the parentheses, right? The B is going to become raised to the square outside that parenthesis. Now we have a 1 here. This n is going to cancel out with this n, the n square, right? It's going to cancel out with this n square. I think I'm doing too much. Let's see. Let me go back. I'm skipping some steps here. I'm gonna go back to what we had. So you can, right? You can. Let's see if I can do that here. Yeah. Okay. Now I can do that. This mu naught goes downstairs because you're gonna have a mu naught square downstairs. This mu naught disappears. This n becomes n squared, so this n squared disappears as well, and all that's left is the b squared. Oops. Okay, and look what we have. That's a similar equation that we had in the book. Okay, the only difference here is that this v is the volume. That's my AL. Okay. Let me copy and paste in the order below, and I'm going to leave AL here so you can follow closely with the book as well. Okay. And okay, good. And what else? Well, we have something else. We have U. If you pass the V to the other side, you know, we are going to have what we had before for the capacitor, which is the energy per unit of volume, which ends up being very similar. Oh, and I'm even going to put B here for the magnetic field so it don't mix up, right? Compare that to the capacitor that we had before. Okay, for the capacitor is half a constant, an electric constant times E squared. Here for the inductor is going to be also a half times a magnetic constant, but it's the inverse of my magnetic constant, times B squared. Isn't that nice? The energy per unit of volume. They are both proportional to the square of the field. Okay? So if you want to do some work with this device or this device, that's the amount of energy that you have stored in them. The resistor doesn't store energy. The resistor just spends energy, okay? It doesn't, but those two devices, they can store energy. Yeah, they can store energy. And they store the energy in the electric field, and the other one store the energy in the magnetic field. The resistor does not store energy whatsoever. It just spends energy, right? P equal to what? Ri squared. Ri squared. Remember that? Vi or Ri squared. What time is that? 11:08. Let's see here. Let's make sure that I gave attendance to everybody. Any questions about that? The next thing that we're going to do, see, is going to be transformers, which are devices that we use every day to convert energy. But let me take a look at my attendance record here first. Let's see. Ashley, are you there? Looks like I saw Ashley coming in. Hello, Ashley. Elika, okay. Okay, Elika is here. Good. Anybody else? Artur Pacheco, are you there? Ashley is not answering. Let's see. And Artur Pacheco, are you there, Artur? Ashley, okay. Thank you, Ashley. And Ashley Diaz, one. Artur Noor, are you there? Noor is still not here in my list. Artur Pacheco is not answering, so he must be away. So let's have our break and we will return, try to finish this chapter today, okay? Break from 11:10 a.m. to 11:25 a.m. I see you shortly. Bye-bye. Okay, I'm back here. And okay, so we have. Oh, by the way, what I didn't tell you about the inductor, right? There is the inductance. Now, the inductance is this new quantity, okay, that has a given. It has a given unit. So let's take a look. Let's take a look at the unit. Let us take a look at the unit of inductance. Okay. We have the unit of inductance. We have the unit of capacitance, right? We have the unit of resistance. We have the unit of inductance. Okay. Well, put that as capital letters here. It's the ohm, right? The unit of inductance is the ohm now. Unit of capacitance is the farad. I'm gonna put the like a capital, some capital Greek here symbol. And then what's going to be the unit of inductance? Okay, the unit of inductance is going to be the Henry. And the Henry, okay, Faraday was what? The Coulomb per volt. That's what Faraday is. The Ohm is what? Ohm is what? V equal to Ri, right? So it's going to be volt per A, per current. Okay, volts per current. And the Henry, what's going to be the Henry? Oh, you gotta look at this equation right here. Okay. This guy here has no unit. The unit of N, right? The number of turns is going to be unit of 1. The unit of flux, magnetic flux, is going to be the Tesla times the area. I'm going to put meter square. And finally, the current here is going to be the unit of amps. That's what the unit of Henry is all about. It shows up so frequently that we call it, and that unit is so important that we call it the Henry, presented by H. Let's take a look here. Unit of inductance, right? Unit of inductance. Okay, Henry, abbreviated as H. Okay, capacitance, Faraday, right? Capacitance, Faraday, and so on. You call that, and now we can move forward. Let's also document what you should know in this chapter for chapter 22. It's 22.1, 22.2, 22.3, 22.4, 22.5. We cover all of that. Yeah, we're going to skip 22.6, 22.7. Skip 22.6, 22.7, 22.8, and 22.9. Okay. No, self-inductance is more important than mutual inductance. Okay, we're going to be using it all the time. Rarely we use mutual inductance out there, but you should know anyway. We did the energy stored, and then we're going to talk about the transformers. So another important device that uses Faraday's law, Faraday's law of induction. So we have the generator. In addition, another important device, in addition to the generator, used by these laws of induction, is the transformer. And we have transformers all over the place. Okay, that electricity that goes from the power lines outside your house needs a transformer to bring down the voltage before it goes into your house. And it's the very transformers are very efficient devices. They can convert AC voltages from one value to another one with very little loss of energy. That's why, it's 99%. And how do they work? How do they work? Okay. Well, is that device of mutual inductance that you saw? Okay, so let's go back to what you saw in the drawing for mutual inductance is a transformer, by the way. Mutual inductance right here. Looks like I gotta move forward. For some reason, let's see. Let me. Okay, good. What you have right here is the principle of inductance. You have a AC generator in a circuit, okay, and this circuit couples its energy to another coil that you have here, and in the process, depending on the number of turns in each device, you can either increase the voltage or decrease the voltage. That's how transformers do. Okay, so you can convert AC voltages from one value to another one. Is very little loss of energy. Say, assume that you have 1,000 volts, 1,000 volt AC in a circuit. You can use a transformer to either step down this voltage, say to 120 volts AC, okay? Or you can also step up or step it up to 2,000 volts AC with very little loss of energy. Okay, so that drawing that you saw is the principle of a transformer. Okay, here you go. What you see here is you do have a sort of a transformer in there, but there are better ways of build a transformer. There are better ways. Let's see if I have here a drawing here. Oh yeah, here you go. See, that's one. What you see here is kind of a transformer. This guy here is the source, the primary, and this other one here is the secondary. It has no source whatsoever, no power source whatsoever, only this one. So this guy can transfer energy to the other one. And if this one is 1,000 volts, depending on the relative number of turns, you can step it down to, let's say, 100 volts here. Or you can also increase it. It all depends on the number of turns. Okay, and real alternators in real life, how do they look like? Let's take a look at not alternators. Transformers, real life transformers, how do they look like? Let's get one here. We have transformers there in the college. Transformer. No, it's not the movie. Electrical transformers. Electric transformers. Three-phase transformer. Let's see. I want something. Okay. I like this one here. Maybe this one. Let's take a look at this one. Okay. Basic transformer with 2 coils of copper wire wrapped around the magnetic core. Okay. Okay, so here you go. Here's a solenoid and here's another solenoid. Okay, that's what we have. You can either do what I showed to you before, right? You can either do something like that, or you can do better than that. There's another way that we can. This is a transformer, like I told you. Or you can do something better than that. How are they doing here? No, you can get a metal and connect those 2 solenoids next to each other. And what does this metal do? this metal, they concentrate the magnetic field of one solenoid, so you can have a better transfer of energy from one to the other. So one is connected to a circuit, the other is just a closed circuit. The one is connected to a power source, the other one is not connected to a power source. Right? So you can transfer electric energy from one to the other. If this one is connected to the power source, you'll be transferring energy from this one to this other one. Okay. So let's see if we, oh, here you go. That's an illustration, that's a circuit illustration of a transformer. You have one coil here, we have the secondary coil here, and then you have this bar in between them, connecting them. It didn't do the whole thing, right? But that's what this symbol means. Okay, here you go. Here's another one. You know, we have a conducting donut, right? A square donut. Usually it's like that. The conducting is square donut. You wrap around the wires on one side, and for your primary device, and wrap the wires around the other side of this device. So all the magnetic flux is transferred from the primary device to the other one within this transformer core. If you were to take out the transformer core out, the magnetic flux would be very small because the magnetic field outside this solenoid would be almost zero, right? So that's the way they found out to build the practical transformers. Okay, so here you go again. And let's see more. Okay, you have an instrument transformer with polarity dot. You cannot see what's inside, but it's something like you saw before in that first picture, right? Let's go back to the first picture. That's how a transformer look like. You know, a metallic core connecting the center of one coil to the center of the other coil. And so any magnetic field in the primary coil is going to be concentrated inside this metallic core and propagate to the other one. So you have induction happening here, okay? And then let's see, here you go, here's the equations. I'm going to write down the equations in a better format for you, okay? So going back here, my notes. We already did something similar before, but I'm going to do that again with the specific goal of illustrating the transformer. So here you go. So we have this primary, the induced electromotive force in the primary is going to be given by the number of turns in the primary times the magnetic flux. Okay, times the magnetic flux. I can even put primary there too. Well, put it. The secondary is the same, just with the letters exchanged. Okay. Well, it happens that the magnetic flux in the primary is going to be equal to the magnetic flux in the secondary, no matter what. No matter what's the diameter of the secondary, okay? It's not going to change in that configuration that you saw, in the configuration of a transformer, in the configuration of the transformer, we have the following. That's we have that the magnetic flux through the primary is equal to the magnetic flux through the secondary. And then we end up having the following relation. We end up having the following relation, VP. VP over VNP. Is going to be equal to Vs over Ns. And now you can see how we can step up and step down the voltage in a transformer. Okay? Don't forget what you have here is a, has that magnitude V prime naught sine of omega t. Here too, you're going to have V prime naught S times sine of omega t, okay? Don't forget that. But the sine of omega t are going to cancel out in both devices, okay? And let's take a look. I'm going to, here you go. What's going to be, I'm going to write that in a different way. I'm going to put the Vs on the left side and the NP on the right side. Okay. Look very closely. Look very carefully at this equation. Okay. Note that if NP greater than NS, NP greater than NS, then VP is gonna be greater than VS, right? Make sense? In this case, we say that the transformer is a step down transformer. Notice the following. One, if, right? Two, now if we have all the opposites, right? Less than the other. No? And then it's step up transformer. We have a step down and step up transformer. Let's do some numeric examples so you can understand that better. Okay. So you can see the numbers, right? Instead of just the letters. Okay, so let's say, example. NP is equal to 330. And NS is equal to 25 turns. Solenoid is 330 turns, and a second solenoid is only 25 turns. Okay. Primary coil. And I'm gonna. Primary coil is just like your. It's 120 volts. Okay. Find VS. Find VS. That's the problem I'm proposing you. And by the way, it's example 14. Okay, example 14 in your book. So all you gotta do is to use this relation right in here. You go, VP is 120 volts. Oh, I'm gonna do it like that. 120 volts. NP is 330 turns, and S is 25, right? So we solve this equation. VS is going to be 120 divided by 330. Times 25. Okay, like that. If you do the math, okay, and it's in the book, we get 9.1 volts. But it's going to be alternate current. You can do that only as, by the way, you can do that only as alternate current, okay? You cannot do that with direct current. This is step down. Keep in mind, huh? Keep in mind that this step up and step down procedure with transformers work only for AC current. It doesn't work for DC. It does not work for DC because you cannot have electric induction with a DC current. Okay, 9.1. What about same example, right? Same example, similar example. Example 14 in the book. Example 14 in the book, okay? 14A in the book. Example 14B in the book, right? What else you need? You need the current for this. Current in the primary. Current in the primary is 0.83. 0.83 amps. Find not the voltage in the secondary, but find the current in the secondary. Here. Okay. Find the current in the secondary. Well, the ratio applies also for the current. Okay. You should have the same ratio for the current. So we're going to have I in the primary divided by I in the secondary. Wait a minute. Let me see one thing. No, it's all the way around. Sorry, it's all the way around. Is the current goes with the inverse. Okay, if you lose in the voltage, you must gain in the current, and vice versa. Okay. And how do we find that out? How do we find that out? Okay, we need a little bit of, okay, I didn't do that here. I'm going to do that for you right now. Okay. Okay, to find how, look very carefully. No. For the current, the process is a little bit different. Recall that recall that there is a relationship between the power, the voltage, and the current, right? Power is equal to VI. But because we are dealing with an AC circuit, okay, the VI here should be the root mean square. Okay, we covered that before, right? And the current also should be the root mean square. Okay. So when we have a transformer, we are transferring energy from one transformer to another. And for that, the case of an ideal transformer, right? The power on the primary transformer should be equal to the power on the secondary transformer. It's very close. It's not exactly 100%. It's like 99%, very close to that. So I'm going to put it P primary is equal to P secondary, which is equal to P, okay? And now instead of having, here should be V root mean square, right? Of the primary. VI root mean square of the primary as well. Okay, and which, by the way, is equal to the V root mean square of the secondary, current root mean square of the secondary. Okay. And now that you have primary, and now we use this equation right in here to get the relations that really matters. V primary over V secondary is equal to I secondary over I primary. Okay. And by the way, we use this equation right in here. So it's the inverse because of this relation. Okay, it's the inverse because of this relation here. And now that we got it, right? Here, the I primary, if we step up, we stepped up, right? Let's see here. No, we step down on the voltage. If we step down in the voltage, we are going to step up in the current. Okay, and here it's going to be I. Let's see here. I secondary, I primary. Yeah. No. This is all the way around. Here you go. No, here you go. I'm going to do this one here. Okay, better now. 0.83 here. Oh no, I'm in the wrong place. Sorry, folks, should be here. Yeah, I was doing it in the wrong place. Okay, that's the right one. I primary is 0.83. .83 amperes, right? I don't want to hear. 0.83 amperes. Okay, I secondary Yeah, now we have it. And then we solve for that, right? We are going to step up on the current. And that's because of conservation of energy. By virtue of the conservation of energy, conservation of the power. So that's instead of 0.83 amps, you are going to have 11 amps. That's item B, 1158. One more minute to go. The average power delivered to secondary coil is the product, blah, 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 right? Okay, let's see what's the C. The average electric power delivered to the transistor circuit. Okay. C. What is the average power? What's the average power delivered to the secondary circuit? There you go. That's what he wants. Okay, so the average power is going to be P. The power, is conserved. So we're going to have V in the primary times I in the primary, or V in the secondary times I on the secondary. Either way works. So doing that for this one, V in the primary that we found before, 120 and 0.83 amps. That can be either way, right? 120 times 0.83, what do we get? Yeah, it's very close to the book. It's very close to 100. I'm getting 99.6. Okay. He's doing, because he's using significant digits, he's getting 100 watts. Okay, so 100 watts. So that's what we have. Any questions? It's at 12 noon right now. Let's see if there is any questions here before we go. We're done with chapter 22. Done with chapter 22, and we start chapter 23 next week. Okay. Yeah, alternating current circuits. Okay. So I see you next week. And by the way, I have office hours now. Thank you. Bye-bye.